Okay, let's dive right into this explainer. Today, we're taking on a really incredible challenge, which is figuring out how to close the gap between sudden human panic and safe, immediate robotic reaction times. So imagine a scenario where someone is using an assistive robotic device like a highly advanced smart wheelchair, and they experience a sudden, terrifying emergency. How does the machine actually know to stop its routine programming and instantly protect the user? Well, we are looking at how we can mathematically bridge that exact gap, literally translating pure, unfiltered human emotion into a concrete language that hardware can act upon without a second of hesitation.
Which brings us to a wildly fascinating question. Can a machine mathematically perceive human despair? Now, I know that sounds like something straight out of a science fiction novel, right? But it's not. By combining Gemini Flash Level 3 speed logic with the clinical psychology of a trauma response, we can actually, mathematically, isolate and detect what researchers call a perception of despair. To be clear, we aren't teaching a machine to feel emotions. We are teaching a machine to rapidly calculate and categorize the language of human panic.
Section 1. The Psychology as Math, Translating Panic into Variables. To really understand how we pull this off, we have to start at the biological foundation. When someone enters a trauma state, complex, future-focused processing words completely disappear from their vocabulary. All that's left are immediate survival or threat signals. You can think of a despair state as a sort of psychological gravity well. Sudden panic violently pulls your most basic, immediate survival instincts to the very front of your mind. Think about it. If you're in immediate physical danger, your brain isn't forming complex, nuanced sentences about what you're going to do next Tuesday. The trauma response strips away all that executive function, leaving only the most urgent, basic words at the top of your mental queue. So, to build an algorithm for this, we just need to mimic that exact biological gravity well. To actually quantify this despair, our algorithm processes language tokens using two primary mathematical weights. We look at the complexity of the language and whether the word is focused on the present or the future. First, we have the complexity score, or C. We assign lower numbers to basic, survival-driven language and higher numbers to complex, abstract thoughts. Then we have the temporal horizon, or H. A score of 0 means the word is trapped entirely in the immediate present, while a 1 means it looks to the future. By scoring incoming words on just these two metrics, we can map chaotic human panic into a clean, mathematical matrix that a machine can read instantly. Section 2. The Sorting Engine. Bubbling up survival signals. So let's see how this builds into an actual algorithmic engine using a Python bubble sort implementation. Now, we don't need to get bogged down in the code itself, because the underlying logic, which is optimized for real-time streaming, is beautifully simple. If a word is low complexity and zero future focus, it physically swaps positions in memory to bubble up to the front of the perception matrix. It's like a continuous rapid-fire sorting mechanism. Step 1, the system continuously scans the incoming stream of spoken or interface language. Step 2, it compares the complexity and temporal horizon of adjacent words. And step 3 is where the magic really happens. The algorithm forcefully pushes those low complexity, immediate present words to the top. It ensures the robot is literally shifting survival words to the very front of its processing queue.
This exact output brilliantly illustrates how the system successfully filters immediate threat signals right up to the top. Words like help and run score 1 in complexity, and they're absolutely not future-focused. So they receive a high despair priority. On the flip side, words like analyze or plan are highly complex and strictly look ahead to the future. They naturally sink to the bottom as a low despair priority. For an assistive interface, this sorted list represents exactly what the machine perceives first. The panic is perfectly isolated and identified.
Section 3. The Physical Reaction. Bridging to Lund University's Juliet language. Okay, so we have the mathematical perception figured out, but how does an assistive robotic device physically react to this sorted stream of despair? It's one thing to sort a list of words on a screen, it's another entirely for a multi-hundred-pound piece of hardware to react safely without any lag. By looking at engineering coming out of Sweden, we find our answer, the Juliet language. It relies on hard predictability to manage robotic safety. Co-created by Lund University and Cognobotics, and actually taught via Lund University's Coursera portal, Juliet is specifically engineered for real-time safety and motion programming. Because when you're adapting robotics as assistive technology, you absolutely cannot have lag and you can't have unpredictable, jerky movements. The underlying math of Juliet relies on strict timing concurrency to close that gap between what the human desperately needs and how fast the robot can safely move to provide it. The crucial takeaway here is that when an assistive mechanical device detects this low complexity, zero future state, it instantly shifts its operational safety profile into hard real-time emergency mode.
The very millisecond that algorithm we discussed bubbles words like help or pain to the top of the stack, the Juliet programming completely takes over. The machine recognizes the human is in a despair state, and it ruthlessly overrides its standard operating procedures to lock into this emergency mode.
And what does that actually look like in practice? The robot immediately stops executing all of its long-term tasks and dedicates exactly 100% of its processing power strictly to immediate protection and survival routing. It drops absolutely everything else. It won't try to navigate a complex path. It won't try to quietly update its software in the background. It dedicates 100% of its capabilities to ensuring the human is safe in that exact moment. Section 4. The future. Upgrading the perception algorithm.
We've successfully built a bridge from purely human intention to fast, safe robotic reaction times. But the underlying architecture can evolve even further. As we look ahead, the ultimate question is whether we expand this into a neural network classifier or if we should start writing scripts directly in Julia and Juliet syntax to simulate how robotic systems handle these real-time safety shifts. Right now, our bubble sort method is brilliantly simple. It's incredibly effective for isolating that despair state based on fixed mathematical weights. But could a perceptron machine learning classifier adapt to individual users, actually learning their unique linguistic panic cues over time? How far can we push the boundaries of real-time robotic safety? It's a profound challenge right at the intersection of human psychology and advanced engineering. So I'll leave you with this. If you were designing the next generation of assistive tech, how would you build the bridge between human despair and robotic action?